Hello everyone. For this tutorial video I'd like to talk about Green's theorem, which is used to relate line integrals to the double integrals we studied earlier. In particular, the exact theorem states, if the curve C is positively oriented or in the positive direction, smooth so it has no discontinuities anywhere, and piecewise, as well as simple so no overlapping parts, and closed, again meaning there are no breaks or openings, then the line integral of the vector field is exactly equal to the double integral of the partial derivative of q with respect to x minus the partial derivative of p with respect to y. There is actually a special symbol for line integrals that satisfy Green's theorem, which is like a normal line integral, except there is a circle intersecting the middle of the integral symbol. And sometimes you will see the circle written as a loop like this with the arrow on the end, but it means the same thing. So if we are told to evaluate this line integral using Green's theorem, and we are specified the region of a triangle with vertices 0, 0, 1, 1, and 1, 2, we would plot out the situation and draw straight lines connecting all three vertices, and see that x is limited between 0 and 1, and y is limited between 0 and 2 times x. So now, because we know that Green's theorem will work for this, we can apply figuring out the p's and q's for the partial derivative, and also using the limits for x and y specified in the graph of the triangle. So now, we simply use methods we already know are true from computing double integrals, and we get a finite answer of 2/3. Even though Green's theorem is stated literally to not work for regions with openings in them, we can be creative and split a region with opening into multiple regions that are closed. Which makes sense if you remember how improper integrals worked from calculus 2. If we ask to evaluate this line integral along two overlapping circles where one is empty space, we would do this by using polar coordinates. Although first, taking the partial derivative in the normal rectangular coordinate system, and then converting it to polar coordinates for the integral. We see, fortunately, we are provided exactly the limits of r, as well as the limits of the degree, because we are told two circles, which we know is rotated from 0 to 2 pi. So now, we simply evaluate the integral as a normal double integral, and get a finite answer of -45 pi over 2. Now that we have figured out how Green's theorem works, we can transition away from talking about line integrals and talk about the final type of integral from calculus 3, which are surface integrals, and are used to calculate surfaces governed by vector fields, similar to how line integrals are used for lines governed by vector fields. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.